The rate constant for the first order decomposition of hydrogen peroxide is given by the following equation. And the given equation is log K equals to 14.34 minus 1.25 10 raised to the power 4 K upon T. We have to calculate the activation energy for this reaction and at what temperature will its half-life period will be 256 minutes. All right. So what is the data that we have? We have an equation, and what is this equation? Log K is equals to 14.34 minus 1.25 into 10 raised to the power 4 K upon T, right? So if you see, and this is the Arrhenius equation in terms of the log, okay? So you know that Arrhenius equation in terms of log can be written as log K equals to log A minus EA upon 2.303. All right, log EA upon 2.303 RT. Okay, so this is what the Arrhenius equation, standard Arrhenius equation in terms of log can be represented, right? Now, if you say that this is the equation 1 and this is the equation 2, now compare the equations and get the values. Okay, so whenever you will compare the equations, what values you will get is, okay, you will get the log A is basically 14.34. All right, log A is 14.34, and this term, that is the EA upon 2.303 R. Okay, so if you see this term, right, so this whole thing will be equals to, that is EA upon 2.303 R. This complete thing is equals to 1.25 into 10 raised to the power 4 K. Okay, so this is the value that we have. Now we need to calculate the activation energy. So to calculate the activation energy, just do the cross multiplication. So this will be your EA 2.303 multiplied by R multiplied by 1.25 10 raised to the power 4 K. All right. Now put the values of the R. So this will become 2.303 into 8.314 joule per Kelvin per mole. All right. Joule per Kelvin per mole multiplied by 1.25 multiplied by 10 raised to the power 4 K. So this Kelvin to per Kelvin cancel out, and this overall calculation, whenever you will do this calculation, so this will be 23933, okay, 0.3 joule per mole, right? So this will be your activation energy in terms of joule per mole. If you want to convert this into kilojoules per mole, so this will be your 239.3 kilojoules per mole, right? So this will be your activation energy. So first part we have solved of this question, that is the calculation of the activation energy. Okay, now we need to calculate the second part, and the second part is saying that at what temperature will be the half-life will be this. It means that it is asking you about the temperature. All right, we need to find out the temperature and the half-life, that is the T half. T half is given as 256 minutes. Okay, 256 minutes. Okay, so remember that this is the first order kinetics, and for the first order kinetics we know that we know that this T half is nothing but it is the 0.693 upon K, that is the rate constant. All right, so from here you can calculate the value of the K, that is the 0.693 upon T half. All right, So if you will do this calculation, then what you will get the K 0.693 divided by half-life is 256 minutes. Okay, 256 minutes. So the rate constant K will be, this will be 4.51 into 10 raised to the power minus 3. Okay, per minute. But instead of this, let me write it once more. This K value in terms of the minutes. Okay, in terms of minute, you will get the value that is 2.707 into 10 raised to the power minus 3. Okay, minute inverse. So this will be your in terms of minute inverse, and if you will convert this into second inverse, then this will be your 4.51 into 10 raised to the power minus 5 second inverse, right? So this is the calculation for the K. Okay, so we have calculated the K. Now again we need to calculate the T. All right, we need to calculate the T. So what I can write over here is, we have the value of the K. So let's put this value of K, in equation 1. All right, so this will be log 4.51 into 10 raised to the power minus 5, right, will be 14.34 minus 1.25 into 10 raised to the power 4 K upon T. Okay, so whenever you will do the calculation and we need to find out the K term, okay, with T, so I can also write this as, how I can write it, this term, all right, 1.25 into 10 raised to the power 4 K upon T. Okay, on rearranging, you will get the value, that is the, what will be this case, whenever you will shift this on the left side. Okay, so this will be a 14.34 minus log 4.51 into 10 raised to the power minus 5. Okay, so just solve this particular thing and you will get this complete value will be 18.688. okay, 18.688. all right, so this will be the now. So once you need to calculate the T. Okay, so what will be the T? So do the calculation, right? Let me write it again. Let me write this number again so that there is no confusion. This value 18.688. okay, this, so this is 1.25 into 10 raised to the power 4 K upon T. Okay, so this is the value. Now in order to find the T, what you will write over here is, okay, 1.25 into 10 raised to the power 4 K upon 18.688, right? So whenever you will do this division, okay, you will get the 668.95 Kelvin. Okay, so this you can round off temperature, that is 669 Kelvin, right? Approx. So this will be your answer for this question. All right, so what we have just did in this particular question is, we have given the following rate equation for the first order kinetics decomposition of hydrogen peroxide, and we just compared this with the Arrhenius equation in terms of the log, and we obtain the value of the EA and log EA upon 2.303 and log A. all right, and from this we calculate the activation energy. Once we calculated the activation energy, we put this, we use the formula for the T half, and T half is this one, and we calculated the K, rate constant K. And once we get the rate constant K, then we put that value of the rate constant K into the given first equation. And from this equation, by solving this particular equation, we get the temperature is 669 Kelvin. Right? Thank you.